If you've been tracking the push to get large language models to solve the abstraction and reasoning corpus, you've noticed a consistent pattern. We keep throwing more synthetic data and heavier supervised fine-tuning pipelines at the problem, but the performance gains are stubbornly plateauing. The real bottleneck is the model's capacity to learn from correct examples. It's its inability to recognize plausible mistakes. Today, we're breaking down DIARC, a new framework that fundamentally shifts how we train language models for abstract grid reasoning. Instead of brute forcing the model with more positive demonstrations, DIARC forces it to distinguish between correct outputs and carefully constructed negative alternatives. The result is a consistent, measurable jump in ARC-like reasoning across open-source backbones, with QN3 hitting over 96% accuracy on ARC-AGI 1 and mini-ARC, outperforming several closed-source systems. Let's start with why the current paradigm is struggling. ARC tasks are designed to test latent rule induction. You're given a small support set of input-output grid pairs, a query input, and you have to predict the corresponding output grid. In practice, these grids are serialized into sequences of integer color indices and treated as next-token prediction problems. The standard approach is supervised fine-tuning. You feed the model thousands of correct input-output pairs and optimize the conditional likelihood of each token. But SFT has three critical weaknesses for this domain. First, ARC output sequences are long, making step-by-step autoregressive prediction notoriously error-prone. Second, SFT optimizes locally, token by token, while ARC tasks are fundamentally global, relying on spatial topology and object connectivity. Third, and most importantly, SFT only provides positive supervision. It tells the model what the right answer looks like, but it never teaches the model what a rule-violating but structurally plausible answer looks like. In cognitive science, learning from near misses is a well-documented mechanism for improving reasoning. DIARC formalizes this for LLMs. The core idea is preference alignment. Instead of just maximizing the likelihood of correct outputs, DIARC constructs preference pairs and trains the model using direct preference optimization. You give it a chosen output, which is the ground truth, and a rejected output, which is a negative sample derived from the same task. The model learns to assign higher relative likelihood to the correct sequence while pushing down the likelihood of the rejected one. But the magic isn't in the alignment objective itself. It's in how DIARC constructs those negative samples. It does this across three distinct levels, each targeting a different failure mode. The first strategy operates directly in the output space through visual transformations. Since ARC is inherently spatial, DIARC applies four families of atomic grid operations to the correct output. Grid block operators like pooling, mode centering, and removing small connected components preserve the coarse layout, but destroy fine-grained structure. Rigid shifts translate the entire grid in 8 directions at different magnitudes, filling newly exposed cells with a background color. This creates spatially coherent but misaligned outputs. Morphological operators like erosion, dilation, skeletonization, and convex hulls thin, expand, or outline objects, while keeping the overall arrangement intact. Finally, local perturbations inject salt and pepper noise or swap boundary pixels. These transformations are crucial because they generate candidates that look structurally valid, but violate the underlying transformation rule. They force the model to learn spatial invariance and rule consistency, not just pattern memorization. The second strategy moves up to the program level using domain-specific language, or DSL. Many ARC solutions are represented as executable transformation programs built from predefined primitives. DIARC analyzes a pool of these programs, identifies recurring local rule patterns across tasks, and applies a greedy coverage criterion to select the most reusable patterns. For each retained pattern, it defines a unified program-level rewrite that acts as a semantic reversal. If the original program maps an input to the correct output, the rewritten program maps that same input to a ruling correct but logically adjacent output. This injects program-level contrast directly into the training signal, teaching the model to recognize when a local transformation step has been inverted. The third strategy uses LLM-assisted task-specific rule editing. Here, an external model is prompted to modify the transformation rule of a given task, constructing an alternative that is as close as possible to the semantic opposite of the original. When a clean reversal isn't feasible, it generates a close alternative that stays near the original logic but diverges in task-relevant behavior. This creates highly targeted near-miss examples. There's a catch, though. When the number of edited tasks is small, these LLM-generated negatives can cluster around a few recurring operation types, like set extraction or bounding box operations, which temporarily biases the model. But as the dataset scales, that bias dilutes, and the model learns a much broader contrast between positive and negative rule applications. Once these preference pairs are constructed, DIARC trains them using direct preference optimization. The objective is straightforward mathematically, but powerful in practice. It maximizes the log likelihood ratio of the chosen output relative to the reference model, while simultaneously minimizing the log likelihood ratio of the rejected output. A temperature parameter, beta, controls how aggressively the model pushes away from the reference policy. In practice, the policy model is initialized from the SFT checkpoint, and the reference model is a frozen copy of that same SFT model. This setup avoids the instability of training a separate reward model, which is notoriously difficult in sparse supervision domains like ARC. The results across 6 benchmarks are consistent. On ARC-AGI 1, ARC-AGI 2, Mini-ARC, Concept-ARC 1 DIARC, and the community dataset, DIARC improves over SFT baselines across 3 different open-source backbones. The gains aren't limited to weaker models. Even with QN3, which already had strong ARC performance, DIARC pushed accuracy past 96% on 3 major benchmarks, surpassing specialized recursive models and several frontier closed-source systems. But where exactly are these gains coming from? The authors decomposed the improvement into 2 channels: generation gain and discrimination gain. Generation gain measures whether the model produces more correct candidate solutions after training. Discrimination gain measures whether the model is better at selecting the correct solution from a pool of already generated candidates. The data shows that DIARC improves both. The model generates more valid outputs, and it becomes significantly better at ranking them. This dual improvement explains why DIARC is highly compatible with test-time scaling techniques. When combined with test-time training, task augmentation, product of experts re-ranking, or depth-first search, the DIARC-enhanced models preserve and often amplify their performance gains. The preference alignment doesn't just help direct evaluation. It makes the underlying policy more robust to advanced inference-time reasoning pipelines. There are limitations, and it's important to be transparent about them. The full negative construction pipeline currently relies on auxiliary resources like ARC task generators, which are well established for ARC-AGI 1, but not yet available for other benchmarks. As a result, the visual transformation strategy is the primary driver for non-AGI 1 datasets. Additionally, the rejected outputs are auto-generated, not human-annotated, so their semantic quality varies. Manual curation or filtering could likely push performance further. But the broader takeaway for AI research is clear. We've spent years optimizing language models for next token prediction on positive data. DIARC demonstrates that formalizing the learning of near misses through preference alignment is a highly effective post-training technique for abstract reasoning. By teaching models not just what the right answer looks like, but what a plausible mistake looks like, we bridge a critical gap between autoregressive generation and holistic rule induction. If you're working on spatial reasoning, program synthesis, or any domain where local token accuracy doesn't guarantee global correctness, DIARC's framework is a blueprint worth studying. The code is open source, the benchmarks are public, and the approach is ready to be integrated into the next generation of reasoning pipelines.